Assalamualaikum everyone, welcome to the course of Real-Time Embedded System. Today we are going to continue our chapter number 6, that is of interfacing, and today is our lecture number 20. So previously we talked about moving data from peripheral to memory with the help of DMA and without the help of DMA, and I showed you all the cycles, what are the control signals that are being sent in case of we are using DMA or in the absence of DMA. So today we will talk about arbitration. Arbitration means dispute resolution. For example, you have one resource available for peripheral and there are multiple requirements for the peripheral. So how we can deal with that situation? So let's start to the topic. So in our earlier discussion, several situations existed in which multiple peripherals might request service from a single resource. For example, multiple peripherals might share a single processor that services their interrupt request. As another example, multiple peripherals might share single DMA controller that services their DMA request. In such situation, two or more peripherals may request service simultaneously. We must therefore have some method to arbitrate among these contending requests. Especially, we must decide which of the contending peripheral gets service, and thus which peripheral needs to want several methods exist. So there exist several methods by which we can do arbitration, means we can do dispute resolution. So out of these methods, number one is priority arbiter. Okay, so you can see here that we have priority arbiter. In priority arbiter, there is a single purpose processor. So we are going to use a single purpose processor which is going to act like a priority arbiter. So you can see here in the diagram that we have a microprocessor, we have a system bus connected to it, and then peripherals are connected to this system bus for accessing microprocessor services. So what we are doing here, you can see here that peripheral is connected to system bus as well as peripheral is connected to priority arbiter. So both the peripheral 1 is connected to priority arbiter through the port interrupt request 1, and peripheral 2 is also connected to priority arbiter through interrupt request 2, and the acknowledgement signal is acknowledgement 1 for peripheral 1 and acknowledgement 2 for peripheral 2. So these are basically the cycles that in first cycle the request will be initiated, in second the request signal will go, in third the priority arbiter will interrupt. So you can see here the interrupt. In fifth we have acknowledgement signal. In sixth the service will be provided, and in seventh we can have data on the data bus or system bus. So peripheral makes request to arbiter, arbiter make request to resource. So in this particular diagram we are not going to access the microprocessor directly. We cannot request microprocessor directly for the service, rather we request the priority arbiter. Okay, priority arbiter connected to system bus for configuration only. So why priority arbiter is connected to system bus? This is just for the configuration, otherwise there is no need. The only purpose of priority arbiter is that if peripheral 1 and peripheral 2 request processor resources at the same time, so we must need to handle this dispute. So in that particular case, priority arbiter will come into action and it will grant resources to peripheral 1 and then it will grant resources to peripheral 2. So let's move on to next slide. As I've told you all these steps, now just go through these steps. Microprocessor is executing its program. So in first cycle, microprocessor is executing its program. It's not mentioned over here in the diagram, but in first cycle, microprocessor is executing its program. In second cycle, peripheral 1 needs servicing. So peripheral needs servicing, so it will assert interrupt request when. At the same time, peripheral 2 also needs services, so it asserts interrupt request 2. Priority arbiter sees at least one interrupt request input asserted. So asserts. So because arbiter is seeing IRQ1 and IRQ2, so it is going to ignore IRQ2, so it will see only IRQ1 and it will assert a signal INT. Okay, so microprocessor stops executing its program and store its state. So as we were doing in the case of fixed interrupts as well as in the case of vector interrupts. So what microprocessor is going to do, it's going to stop its execution and it will store its states. States can include registers, state can include program counters. Now microprocessor asserts acknowledgement signal, that is interrupt acknowledge. So microprocessor will send on the 5th clock cycle acknowledgement signal to priority arbiter. Priority arbiters assert acknowledgement 1 to acknowledge peripheral 1. So now you can see that we are only acknowledging the request of peripheral 1. So in 6th cycle, the priority arbiter will acknowledge the request of peripheral 1. Peripheral 1 puts its interrupt address vector on the system bus. So in that particular case, the peripheral 1 will put its interrupt address vector on system bus. Microprocessor jump to that particular address of interrupt service routine, read data from bus, execute and returns, and completes handshake with arbiter. So handshake means that we are going to acknowledge that everything is being done. Microprocessor resumes executing its program. So we will deassert all this signal and microprocessor will resume its normal program after servicing the interrupt from peripheral 1. So that was about priority arbitration. So let's move on to next slide. So basically there are two types of priority arbiter. Number 1 is fixed priority, number 2 is rotating priority. Fixed priority, each peripheral has unique ranks, as we have seen previously, like each peripheral has unique rank. Highest rank chosen first with simultaneous requests. So for example, we have two peripherals and both of them simultaneously request servicing from the processor. We are going to choose, in fact the priority arbiter is going to choose the one with highest rank. Preferred when clear difference in rank between peripherals. So we usually prefer this type of arbitration when there is a complete or clear difference between the ranks. It's not like if we have like two peripherals at the same rank, we are not going to use this arbitration. Okay. Whereas in rotating priority, it's also known as round robin technique. Priority change based on history of servicing. So we are going to change the priority on the basis of history of servicing. So if some peripheral is getting request servicing from the processor very frequently, we are going to give it more weightage. Better distribution of servicing, especially among peripheral with similar priority demands. Okay, so we are going to provide better distribution to the peripheral with same priority demands. So in that particular case, the priority is changed based on the history of being serviced. Let's move on to next slide. So in addition to priority arbitration, we have daisy chain arbitration. So arbitration done by peripherals built into peripheral or external logic added. So it is basically done on the hardware level. It is built permanently on the peripheral, or we add some external logic. Request input and acknowledgement output added to each peripheral. So we are physically going to add these two things, request input and acknowledgement output. So peripheral connected to each other in daisy chain mirror. One peripheral connect to resource. So as you can see here, we have this resource, that is our CPU, and one peripheral is connected directly to the resource. All other connected upstream. So this is upstream, this is downstream. Peripheral requests flow downstream. So peripheral requests always flow downstream. Okay, this way towards the processor. To resource. Resource acknowledgement flow upstream. The resource acknowledgement, it will flow this way from peripheral 1 to peripheral. Closest peripheral has highest priority. So you can see that peripheral 1 will have highest priority, and it is similar to our fixed arbitration. It's just like we have peripheral 1 with acknowledgement in and acknowledgement out, and then we have request in and request out. Why we have request in? Because the peripheral 2 will send its request to peripheral 1, and then peripheral 1 will send out the request to processor. Likewise, when we are having the data processed by microprocessor, the request will acknowledge in peripheral 1, and then it will out through acknowledgement 2 to peripheral 2. So acknowledgement in. So we have two ways, upstream and downstream. Upstream means that we are moving from processor to peripheral 2. Downstream means that we are moving from peripheral 2 to microprocessor. Okay, so this is daisy chain arbitration. In these daisy chains we have like assigned priority. So priority is fixed. Okay, so arbitration is built onto the peripheral. So you can see that we have these four signals coming in and out, and peripheral 1 has highest priority because it is connected directly to the processor. Peripheral 2 will send a request to peripheral 1, and peripheral 1 in return send the request to microprocessor for servicing by the processor for peripheral 2. So let's move on to next slide. So in this slide we're going to talk about the pros and cons of daisy chain arbitration. As you can see here in this figure, that is on the right side we have daisy chain arbitration, and on the left side we have priority based arbitration. Okay, as I have told you. Now, what are the pros and what are the cons? Easy to add, remove peripheral, no system redesign. So you can simply add or remove the peripherals. Like for example, we have hundreds of peripherals connected to system 1, so we can directly add or remove. We do not require any system design, as in the case of priority based arbitration we must require system design, as we are going to use priority arbiter. Does not support rotating priority. So it does not support rotating priority because the priorities are fixed here in daisy chain. However, the main disadvantage of this daisy chain arbitration is, for example, if any of the peripheral goes down, it will result in loss of access to other peripherals. For example, if we have like here we are just showing two peripherals. So what if like peripheral 1 goes down? So it will cause loss of access. So peripheral 2 won't be able to access or request services to the microprocessor. Okay, so this is the main disadvantage of daisy chain. And the second one is that it only supports fixed arbitration. It does not support rotating priority arbitration. However, adding or removing the peripheral is very easy. We do not require any system redesign. Let's move on to next slide. So another type of arbitration is network-oriented arbitration. So in that particular arbitration, when multiple microprocessors share a bus, we sometimes also call it network. Arbitration typically built into the bus protocol. As you have seen that in previous case we have arbitration built onto the peripheral, so in that particular case we are going to build arbitration into the bus protocol. So separate microprocessor may try to write simultaneously, causing collisions. Data must be resent, so whenever separate microprocessor try to write simultaneously, we can have collisions. So we need to send data again. Don't want to start sending again at the same time, and we do not want processor to send data to peripheral at the same time. So what we can do, we use statistical methods that can be used to reduce the chances of collision or chances of sending data at the same time. Now, typically used for connecting multiple distinct chips. So why we use network oriented arbitration? So we want to connect multiple chips. So for that purpose we use this arbitration. So used to connect multiple on-chip processors. So for example, we have multiple on-chip processor and we want to connect them. We use this network-based arbitration. So in this slide we are going to talk about the vector interrupt using interrupt table. So this is similar to the one that I've already told you. So we have a processor, we have priority arbiter with these signals mask, RDX0, RDX1, and then we have enable signal. It is connected to only the diagram direction is changed, rest of the things are same. So this is peripheral 1 with data, peripheral 2 with data, and these peripheral are connected to memory bus, and this memory bus in turn is connected to processor, and then the memory bus is connected to memory where we have the jump table, or we can say that we have interrupt table where the interrupt service routines are written. So let's talk about the points of this vector interrupt using interrupt table. So fixed priority, as we can see here, peripheral 1 has highest priority, it will have highest priority. Keyword underscore at, as you can see here, we have at, followed by memory addresses forces compiler to place variable in specific memory location. So what we are doing, we are placing these variable arbiter mask, arbiter's channel 0, arbiter channel 1, arbiter enable, peripheral data 1, peripheral 2 data, interrupt lookup table. We are saving all these at specific memory location. Now a peripheral index into interrupt table is sent to memory map register in arbiter. So what we are doing, we are basically, so this index, this is the address arbiter channel index. So a peripheral index into interrupt table is sent to memory map register to register in arbiter. So we are sending this address to arbiter. Peripheral receive external data and raise in interrupt. So whenever peripheral 1 or peripheral 2 is going to receive data, it is going to generate an interrupt, and this interrupt will be serviced by priority arbiter. Okay, so this is the code. You can see here that we have this void peripheral interrupt service routine. We have assigned character data. Data is being placed on peripheral 1 underscore register. Do something with the data. So we are doing something with the data. This is for peripheral 1. This is for peripheral 2. The same thing. Unsigned character data. Data is equal to peripheral 2 underscore data underscore register. Do something with data. And here we are initializing. So this is the call for initializing. Void initialize peripherals. So enable both channels. So in masking we enable channels. In arbiter 1 we have the address for, as I have told you previously, that peripheral index into interrupt table. So RDX0 basically contains the address of the interrupt service routine in the memory or in the jump table. So it has 13 address, the channel 1, and channel 0 will have its ISR at 13, whereas channel 1 has its ISR at 17. So you can see here interrupt lookup table 13 for channel 0 and interrupt lookup table 17 for channel 1. So these are all the assignments, and for like if we have to access this priority arbiter, whenever data is ready on the peripheral 1 or peripheral 2, they are going to initiate or interrupt requests. So our priority arbiter will be enabled. So it means that enable register will have 1 in it. Okay, so we need to set this pin high. Okay, so this is our main program. So this is how we can initialize our priority arbiter. Okay, so initialize peripherals. So in this initialize peripherals, we are going to assign these values, and then for main program goes on. So as long as we do not have any interrupt, we will not do anything. Otherwise, we will go into ISR 1, that's peripheral 1, or we will go into peripheral 2, depending upon what interrupts occurs. Okay, so that was about using the priority arbiter with interrupt table. Okay, let's move on to next slide. So in previous lecture we talked about DMA, direct memory access controller, in detail. When peripheral wants to send data to memory, so we can use DMA controller, so we do not have to initiate any interrupt like we were using standard IO, we were using memory mapped IO, so we do not have to use all these interrupts. Rather, we can simply use direct memory access using vector interrupt to send data from peripherals to memory. So this is typical Intel 8237 DMA controller. As you can see here, we have request 0, it has acknowledgement 0, request 1, acknowledgement 1, request 2, acknowledgement 2, request 3, acknowledgement 3. So it means that it can service 4 different peripherals, and then we have this data bus from 0 to 7, so it has 8-bit data bus. So address bus is of 20-bit. Then we have address latch enabled. This is memory read signal, this is memory write, this is input output read signal, this is input output write signal. Then we have HLDA, which is basically hold acknowledged, and then we have HRQ, basically hold request. So this is the description, and this particular Intel 8237 DMA controller is basically used with ISA bus. So for ISA bus we need all these address latching, memory write, memory read, IO device read, IO device write. So see the bus ISA bus description in the chapter for complete details. So I have already shown you some examples of ISA bus, like the clocks, the cycles, the channel ready signal, and the other signals that we have there in industrial standard architecture of system bus. So let's move on to next slide. So in this slide you are shown with 8259 programmable priority controller. So this is the priority controller. So you can see that it has interrupt request 0 up till interrupt request 7, so it can handle like up to 7 or in fact 8 peripherals. So you can see here an interrupt request is executed by the peripheral devices when one of these signal is asserted. So whenever any of the signal is asserted, either it's IR0, IR1, IR2, so the request will be asserted. And here we have 8-bit of data bus, we have 0-bit of address bus. This pin acts in conjunction with read-write signal, so we are going to use this pin as a read-write signal. It is used by 8259 to decipher various command words the microprocessor writes and status of the microprocessor wishes to read. So we do not have like any address because we use priority controller for interrupt servicing routine. So we are just putting the data on the data bus. So we use this pin for read-write signals. Then we have a separate pin for read signal asserted. Then we have WR for write signal asserted. Then we have INT. So this signal is asserted whenever there is a valid interrupt request, and INT is interrupt acknowledgement. And then CAS 2 to 0 is basically these are cascaded signal to enable multiple 825. So if you have another 8259 chip, so you can connect with this pin. Okay, so for cascaded connection of this chip with another chip, we can use this pin. Finally, we have SP/enable, which is the function is used in conjunction with CAS connection for cascading purpose. So this is basically for enabling and for the control of the chip that is connected in cascade with this chip. So we can say that for controlling the cascaded chip, we have this function SP/en. Okay, so CAS stands for cascaded signal basically. So that was about the priority controller chip 8259, and this chip is programmable. Let's move on to next slide. So finally we have multi-level bus architectures. As you can see here that we have processor bus, which is local bus, and then we have peripheral bus. The processor local bus is connected to a microprocessor, cache, memory controller, and DMA. And then we have a bridge that is connecting basically these two buses, peripheral bus and microprocessor local bus. On peripheral bus we have various peripherals. So why we are having these two multi-level bus architecture? Let's talk about it. We don't want one bus for all communication. So first of all, we don't want one bus for peripherals and one bus for microprocessor, cache, microcontroller, and DMA. Peripheral wouldn't need high speed. So as you know that peripheral don't need high speed. Processor specific bus. So we do not need processor specific bus because processor specific bus requires more power, it is most costly, and it has excess gates. So if we have too many peripherals connected to processor specific bus, it is going to slow down the bus. So processor local bus is high speed, wide, most frequently communication is done through this processor local bus. Connect microprocessor, cache, memory controller, and etc. Whereas peripheral bus, it's lower speed, narrow, less frequently used in communication, typically industry standard architecture for portability. So the architecture of this peripheral bus is ISA. And bridge is basically your single purpose processor that converts communication between buses. So it converts processor local bus communication into peripheral bus, and also peripheral bus communication into processor local bus communication. So this is multi-level bus architecture. Thank you very much. So that was about today's lecture.